2 sections in one. Give it a quick little flip through the next 2 pages. You'll notice something. There are no examples written in this chapter, in these 2 sections, because a lot of this is just information that we need to be able to use. So what we're going to do in the notes portion of today's class is we're just going to go through this information and highlight the important things, maybe remember some things. All of the examples you're going to do with a group on the whiteboards. You can add additional information to your notes with post-it notes when we get there, but all of our information today is just kind of like going back over content that you would have seen previous to this course. So first things first, functions versus relations. So a relation is any set of ordered pairs. It could be numbers, it could be different things. But the first number in each set, the first component of any ordered pair is called the domain. The second number, the second component in any set of ordered pairs is called the range. So we have 2 vocabulary words coming back for us today, domain and range. When we have ordered pairs, it's just the first terms and the second terms. But specifically, when we are talking about a function itself, a function is a correspondence between this domain and range, such that each element in the domain corresponds to exactly one element in the range. So what you would have said before this class with all that fancy language is that the x's do not repeat, and that's exactly what this is. The x's, x values do not repeat. That's the rule for a function. Second idea is function notation. Again, when we're talking about functions, we're going to give them names. These names are always letters, like lowercase f, g, h, or capital F, G, H. Any letter can be used, but when we're reading them, they look like this, f of x. It tells us the name of the function and the input value, which in this case is x. But f of x, that output right there, represents the value of the function at that number. So it's outputs. F of x is equal to outputs. When we're looking at graphs or functions, a lot of times there's just an arrow indicating that the graph extends indefinitely in either direction. But if you happen to have a closed dot on the end of a graph, that means the graph doesn't extend beyond that point, but the point belongs to the graph. On the other hand, if you have an open dot at the end of a graph instead of an arrow, the graph doesn't extend beyond this point, but that point doesn't belong to the graph. So that's an inclusive versus exclusive notation. Kind of going back a little bit more to whether something is a function or not, we can look at a graph to determine this with the vertical line test. The vertical line test, VLT, all we will do is we will make sure that no vertical line can cross the graph more than once at a particular time. So have we heard of the vertical line test before? Yes. Cool. We're going to be using that today. So again, yeah, we have just a ton of information today to go over in regards to functions and their graphs. For example, let's dive back into domain and range. We said from a coordinate point standpoint, the first component in any coordinate point is the domain, and the second coordinate point in anything is the range. When it looks at a graph, the domain corresponds to the set of inputs that we can use along the x-axis. Now I know my color, because this is color-coded for me and I switched the colors, I'm talking about the domain being here. These numbers from -3 to 2 is where this semicircle shows up on this graph. For the range, we're looking at the y-axis numbers. The y-axis, the semicircle shows up, the lowest point is 1, the highest point is 4. So when we're writing an answer for domain and range, we will want it in both set builder, which is this one, or in interval notation. So you can zoom back to 1.7 if you want to remember where these symbols come from. But these are just the numbers from the graph where we're looking at the domain numbers on the x-axis. So there's x's from -4 to 2. Or the range, which is the y-axis from 1 to 4. We'll be writing both set builder and interval notation domains and ranges for my class, going back and forth between the two. Does all this sound like things we've learned at some point? Yeah, okay, cool. Identifying intercepts from a function's graph, really super simple. If we're looking for the x-intercepts, or what I might call the zeros of the function, we are literally just looking for where the graph crosses the x-axis. Same vibe, but for the y-intercept, it's where the graph crosses the y-axis. The two things I want to point out to you, though, is that when I'm asking about x-intercepts, I may be asking it as where f of x is equal to 0, where the function is equal to 0. If I'm asking about the y-intercept, I'm asking what is f of 0. Do you see the difference in the placement of those zeros? In the top one, when I'm finding the x-intercept, the function is equal to 0. Here, this says plug 0 into the function. That's the difference. Now, important to note that a function can have more than one x-intercept, but it should only have one y-intercept. It might not have one. It can have at most one. Because if it had two y-intercepts, it would have two repeating x values, and it would no longer be a function. We're also going to need to be able to describe portions of graphs that are acting in different ways. If we're talking about where a function is increasing, I'm literally just wanting to know the sections of the graph where it rises from the left to the right, where if you were walking along it, it would be walking uphill. Decreasing, on the other hand, I'm looking for places where the graph is going down, is falling from the left to the right. If we were walking along it, we'd be going downhill. If I ask for where is a function constant, constant just means that it's flat. You will describe these different portions, the increasing and decreasing intervals, using x values. So maybe write that note to yourself. You use x values to talk about the intervals where this happens. From what x to what x. That's where it is increasing or decreasing or constant. We're using the x values like the domain. There's so many things we can talk about when it comes to functions, including the relative maxima and relative minima, which is a plural version of maximum and minimum. That's how you make those words plural. The points at which a function changes from increasing to decreasing or vice versa can be used to find any relative maximum or minimum of the function. If you are changing from decreasing to increasing, we create what's called a relative minimum. If you're looking for where you change from increasing to decreasing, that's a relative maximum. So if I looked at this example here and I color-coded it by increasings and decreasing, I would say right here it's increasing in that center. This section is decreasing and this section is decreasing. So I have two minimum, or I have a minimum and I have a maximum. I have two extreme moments because I am changing from decreasing to increasing, that's a minimum, and increasing to decreasing, that's a maximum. Just a little side note, sometimes the word local is used instead of relative. They mean the same thing. So relative minimum, relative maximums, same thing as local minimum and local maximums. I know I'm throwing a lot at you and you're going to practice on your own. So just highlighting things that are important for us is what we're doing right now. If I'm asking you to check what kind of symmetry a graph has, visually it makes a lot of sense. If you're symmetric to the y-axis, that means you could put a line down the center of the y-axis and it would fold right on top of itself. Do you see how the right side and the left side are right on top of each other? That is symmetric to the y-axis. Symmetric to the x-axis, same vibe, but the x values, we can fold this graph. They would land on top of each other. But when I'm talking about being symmetric to the origin, it's like you put a pin in the origin and you rotate the graph around itself where it would match up one side to the other. That's being symmetric with respect to the origin.
Is that like diagonally?
Kind of. It's a reflection over the line y equal to x, so it's a flip over the x and flip over the y. So you can kind of think of it like that. I like to think of it as spinning. So if you put a pin in the origin and you were to spin this graph around, here I'll get rid of these lines. So put a pin right here and spin it this direction. Wouldn't this side end up on top of this side? That was symmetric about the origin. Put a pin in it and spin it. But of course, we won't always have a graph showing for us. So to test these things mathematically, what you will do is you will substitute in for the y-axis. You will substitute in negative x for x in the equation and resolve the equation. If it looks the exact same, boom, done. Same vibe, but for y, same vibe, but you change both x's and y's to negative and solve. You will see an example of this on the level, so if that is confusing, I will come over and help. I got you. But talking more about symmetry, we can get a little bit more detailed because even and odd functions are particular symmetries. If a function is symmetric to the y-axis, we actually call it an even function. It has a more specific name. And if a function is symmetrical to the origin, we call it an odd function. This is not the degree of the function, this is their symmetries. To check analytically if a function is even or odd, what you will do is you will plug in negative x and you will resolve the equation. If it looks the exact same, the function is even. If it looks the exact opposite, it is odd. Odd, opposite, origin. All of those words go together. Odd, opposite, origin. And that's the first little chunk about functions. The last page here is still something to do with functions, but for up till this point, you probably have at least heard these words, these terms before, and we will practice them together. But these last two bits right here, a piecewise function and the difference quotient, may be newer to you. A piecewise function, I like to call a Frankenstein graph, is defined by two or more equations over specified domains. So if you look at this picture right here, we have this constant moment, and then we have a linear moment. That is two separate equations controlling this entire graph. That's called a piecewise function. A piecewise function is written like this, where you have f of x, or in this case c of g, equal to the first part with the domain where it exists, so between 0 and 15, this would be 40, and then the other equation and the domain with which it exists. So if you see between 0 and 15, it's always 40. But the moment we switch off of 15 on the x values here, we start having this linear equation. So we're trading off which equation is in charge. That means that you have to pay attention to what kind of equation I'm wanting. If I say, please find c of 10, is 10 between 0 and 15 or bigger than 15? In between. So I'm going to use this guy. The answer is 40. There was nothing to plug in. But when I ask you to find c of 45, 45, isn't that bigger than 15? Yeah. So that means I'm going to take the bottom equation and use that one. Since there's a g here, that means I'm going to plug in 45 where g was. Calculate, bing, 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 you get 58. So when I'm asking you to evaluate them, you have to decide whether you plug it into the top or you plug it into the bottom. And it has to do with what number I'm asking you to solve. 10 is between 0 and 15. 45 is bigger than 15. Yes? That's a piecewise function. They're Frankenstein graphs. The last little bit here is called the difference quotient. Now, the difference quotient may probably be 1,000% new to you. So let's look at what the difference quotient is. This entire equation right here is called the difference quotient. It will eventually help us solve things in regards to slope. And if you ever take a calculus class in your life, it will look very familiar to the old-fashioned definition of a derivative when you add limits to it. But we're not doing that. We are just evaluating the difference quotient for different problems. You're going to do it in two parts. Okay, this is the only one that has a really long example, but it's worth talking about. And you'll forget it, and then when we get to this example on the levels, I'll come back and help you. Okay, if we do this in two parts, the first thing I want to evaluate is f of x plus h. The reason I'm doing that is because f of x plus h is a part of the bigger difference quotient. It's easier to solve that one separately than with everything else. So if you watch me trying to solve f of x plus h, that means to take x plus h and plug it into the equation for this problem everywhere there was an x. So do you see how I put x plus h here? And I put x plus h here. See how I substituted that in? Yeah? At this point, I have to just start doing some algebra. This right here is x plus h times x plus h. So I did FOIL. And I got my next step. You might have to show a little bit more work to FOIL, but that's okay. From here, I'm going to distribute this minus inside here. The next step is to distribute this 2, since I have to distribute that to everything right here. And I've got it fully factored out, fully multiplied out for that next step. Are there any like terms that can go away in this? I see I have an x squared, I have an xh, I have an h squared, I have a regular x, a regular h, and a common number. Is there any of those that are the same? No. So we pause. That is f of x plus h. I'm going to take this entire thing, and this is where highlighting might become nice. This entire thing is f of x plus h. So if you notice, I plugged it in this equation where f of x plus h belongs. Do you see how I just put it there? And that's also why it's nice to do that part first, because it's a part of a larger question. Then right here, it says f of x. I've just taken the regular f of x function and I put it there. Do you follow? Okay, then comes some algebra. This first step, all I did was distribute this negative. So all of those signs change. And then all of a sudden, the problem got way smaller. How come? What happened from this step to this step? A lot of things disappeared. Why do they disappear? A lot of them cancel each other out. We have like terms now. We have a 2x squared and a negative 2x squared. I combine them together. They are like terms, but they cancel. I have a regular x and I have a positive regular x. So negative and positive cancel out. I have a positive 3. I have a negative 3. A lot of stuff cancels very quickly. And boom, we have the third line. What did I do to go from the third line to the fourth line? Backwards distribution, which is called factoring. I took out the GCF. It's like I did reverse distribution. I took out an h from each problem. And then how did the denominator disappear? Ah, bow, bow, they're gone. This is the evaluation for the difference quotient for this problem. It's got a lot of algebra skills in it, but they're all algebra skills we've practiced. Factoring, multiplying, combining like terms, distribution. We've got this. Okay, whoa, what happened? We just did so much in so little time. We need to practice these different things and make sure we can talk about functions appropriately. Obviously, there was no examples in your notes today. All of your examples that you're going to work on are going to come from levels that you'll do with people around the room. Now, my recommendation, and I'm going to assign your groups today, so pause for that. My recommendation is to solve the different problems on each level, and if they're like way too easy, you didn't even question it, don't write anything extra down. Just write notes to yourself that will be helpful. But if you're doing a problem where you're like, whoa, I got lost for a second, I forgot this, that, or the other, take a post-it note from the center of the table, and I want you to write a post-it note to yourself and stick it in your notes in the appropriate section. So you're adding extra things to your notes to make them very helpful. Should you write every single question down? No, some of them are way too simple. You will get it automatically. But the ones that make you pause, write some extra things down for yourself. Make your notes useful. Okay?